Welcome everybody to the second part of lecture number 2. In this lecture we'll be talking about further vector operations, and at the beginning I would like to talk about vector decomposition. Vector decomposition means expressing a vector, general vector, into two or more components that are of certain relation or does have certain features that would simplify the mathematical manipulation or the mathematical expression. For example, I think many of us would have seen this before. If we have a vector in the xy plane, like v vector, we know how to decompose it into like x component and y component, and for many problems that would solve like what we are behind or what we are searching for. Also, sometimes when we have like a inclined surface like this one and we have a vector like the red one, we can decompose this vector into two components. One of the components parallel to the surface or tangential component, and one component that is perpendicular to the surface, and this would facilitate the equation. For example, if this vector is the weight, this like tangential vector is related to the friction, and this perpendicular vector is the amount of pressure this green object is putting on the surface, so on and so forth. So the decomposition of a vector into like two or more components is like a technique that we use it frequently to solve and simplify operations. So just keep this in mind because we're going to use this shortly. Okay, so some other vector product relation is the scalar triple product, which is the dot product of a vector with the cross product of two other vectors. So this one, A dot B cross C, of course we do the B cross C first, we'll have a vector, then dot product the vector with A. So this relation can be expressed as B dot CA or C dot AB. And this relation, of course, it's a vector cross product with a vector, because, sorry, dot product with a vector, cross product will produce a vector. So this is a scalar quantity, and this relation equals the volume of the parallelepiped. So this shape here, like that we can build from the three vectors A, B, C, the volume of this parallelepiped equal A dot B cross C. Another vector triple product, which is A cross B cross C, but B cross C is within the bracket. So we do this operation first, then cross product A with the result of the cross product, which is another vector. So this relation is A cross B cross C between brackets would equal B multiplied by A dot C. A dot C is a scalar, B is a vector, so this term is a vector, minus C multiplied by A dot B, which is a vector multiplied by another scalar quantity. So the right hand side is a vector, of course the left hand side is another vector. So this relation is called back cap, so just the letters back cap. You don't need to memorize this, but it's just like you need to know about them. So now we would have an example that we need to prove this back cap relation. So this like rule or this vector relationship between three vectors, we need to prove it. So this example is long, a little bit complicated, but it is very useful in like sort of like an intense kind of example in vector manipulation. So I would expect every student to go through this a number of times till you understand the operation. and we're going to use the vector decomposition heavily into this example, and we also going to use the properties and features of the dot product and cross product in this example. So it's very, very important to understand the details and the manipulation of vectors in this example. So what we are behind is this rule. We need to prove this rule. So B and C are vectors. So any two vectors would define a plane. So B and C, let us say they are on the surface of, or like defines the plane of the surface of your disk or something like that. So the cross product must be perpendicular. The cross product is a vector, or it will be in the direction that is perpendicular to this plane. So it is perpendicular to B, it's perpendicular to C, and of course it is perpendicular to any vector in the plane defined by BC. And this, let us say, the unit vector in the direction of the cross product B cross C is like denoted as AN. So now for A, let us decompose A into two components. One component that is parallel to the BC plane or BC surface, and the other component is perpendicular to it. So the parallel component would be in the BC plane. The perpendicular component would be normal to this plane. So we can decompose A into two components, A parallel and A perpendicular. Parallel means parallel to the BC plane, perpendicular means perpendicular to the BC plane. So we know that the cross product B cross C would be normal to the plane. So this relationship is A parallel cross AN plus A normal cross AN. So this is the distribution property of the cross product. But AN and A normal are in the same direction. So we have the relationship of the cross product for two vectors in the same direction equals 0. So this relation here, A cross the output of B cross C, would end up to be A parallel, which is a component in the BC plane, cross product with them. Okay? So we can just draw A parallel to be somewhere into this plane, and we'll assume it has an angle theta 2 with C, angle theta 1 with B. Okay, let's continue. So we can write B cross C as, we know the like magnitude of the cross product, BC sine the angle between B and C, which is theta 1 minus theta 2. And this is in the direction of AN, where AN is the vector perpendicular. So this is AN going out of the screen. This is the direction perpendicular to the BC plane. So we can write it like this. So the cross product here, A parallel cross product with AN. So A parallel is in the, let us say, the surface of your disk. AN is normal to the surface of your disk. We know that the output of this cross product must be perpendicular to both of them. So it makes 90 degrees to both of them. So because it is normal to AN, it must be in the plane of BC. So it is on the plane of your disk, and it must be perpendicular to A parallel. So if this is A parallel, the direction of this cross product must be 90 degrees normal to this A parallel, and it would be like this AD. So the cross product here would be A parallel cross product with AN, and we denote this as AD. and AD of course must be in the BC plane. So just do some like algebraic like manipulation. The sine of theta 1 minus theta 2, it can be just like expanded like this. So the cross product here of A cross the bracket of B cross C would be in the direction of AD. The magnitude is A parallel, B, C, then this trigonometric function. We know that AD is parallel to A parallel, and of course it is it's normal to A parallel and normal to AN. And of course AD is in the BC plane. So now we can write it this way. So we just like, again, mathematical manipulation. And here, this relationship here, A parallel C cosine theta 2. So A parallel is here. Cosine theta 2 is the angle between like the two vectors, A parallel and C. So we can write this expression as A parallel dot C, and this expression as A parallel dot B. So we're just like doing some algebraic relation now. So we take this term and sort of like say it's equal A. So we just put it in this expression. So let us continue. So now also we need to know that sine theta equal cosine pi over 2 minus theta, and we're gonna use this shortly. So from the expression B sine theta 1, it's equal to B cosine pi over 2 minus theta 1, which equal to B dot AD. So let me grab this picture again here, one moment. I just want to bring this picture with us in this slide as well, so that we can follow easily. Okay. So here, so when we have sine theta, which is this angle, it equal cosine 90 minus theta. So the angle theta here, theta 2 is the angle between C and A. It is the complement of the angle between C and D. So B sine theta 1 equal B dot AD. This is theta 1. So sine this angle equal cosine that angle here. Let me grab my laser pen again. So which is the projection of vector B along the direction of AD, because AD is a unit vector. So the result of this operation is B cosine the angle between B and D, which is the sine between B and A parallel. Same thing for C. So now we can write this expression as such. So this is a scalar quantity, this is a scalar quantity, and this is a vector. So we can now write it this way. Okay. So now let us take the AD as a common factor outside. We'll have this expression. So this is a vector, dot product with AD, it gives us a scalar. It is in the direction of AD. So this is the direction of the cross product. So now this vector dot product with AD is the projection of this vector in the direction of AD. We know that AD is perpendicular to A parallel. So now let us just, we're going to see why is that. Calculate the A parallel dot product with this vector. Just to go with the operation, you will find out this equals 0 when two vectors are having the dot product of 0, it means that the two vectors are perpendicular to one another. This is one of the properties of the dot product. So if A parallel is perpendicular to this vector, so A parallel must be, we know that A parallel is in the same plane as D, so A parallel must be perpendicular to this vector, and because it is perpendicular to AD, so this expression here, which is a vector, must be in the direction of AD. So now A parallel is perpendicular to this expression and it is in the BC plane, so this expression must be in the AD. So the expression now of A cross B dot C will equal this expression. Why? Because we have like this expression dot product with AD, which is the projection of this vector in the direction of AD, and this magnitude is in the direction of AD. Because this vector now we just proved it is in the AD direction, so this like AD and this AD will cancel because this one is in the AD. So just like the magnitude of this vector is in the AD direction, so this will be 1. The result will be the magnitude of this expression in the direction of AD. So this AD and AD will, just like if we remove it, will have the same expression. So now we just proved that A cross product with this bracket would equal this expression. So the expression here now does have A parallel. What we want to prove is does have A. Remember that we decomposed A into two components, A parallel plus A perpendicular. So if we just replaced A parallel with A parallel plus A perpendicular and dot product with C, what will be the result? The normal component is normal to the plane. The dot product of this component with C, the dot product, two perpendicular vectors, it will be 0. So if we like add A normal here, nothing will change because what we add will add 0 because it's perpendicular to C, similar to here. So if we put A parallel or A, it would give us the same result because the added component is perpendicular to the whole plane, so it's perpendicular to any vector in the plane, so it is perpendicular to C and B. Now we just proved this relationship. I know this example is a little bit long, but it's very good in using many of the properties of the dot product, the cross product, the decomposition. Like, so it's sort of like it's an inclusive kind of example. I would appreciate if every student just study this example for a couple of times and make sure that you understand the steps and the logic of all the operations that had been done. So this is the end of part 2. In this lecture number 2, we learned the attributes and differences between scalar and vector quantities. We learned the vector addition and subtraction. We learned the vector product, multiplication with a scalar, dot product, cross product, triple products, and we have this example that sort of like include all what we learned into this module. So thanks everybody, and meet you in the discussion session.